Hi, this video covers the linked list based stack. So what we're going to look at is implementing the stack abstract data type using a linked list. We're using the adapter approach. Remember that an adapter is a container that uses a pre-existing container data structure to implement a new different interface. So what we're doing here is a linked list based stack. That means that we're using the pre-existing linked list data structures that we covered earlier to implement the stack operations. So those would be top, push, and pop. We already have linked lists with push front, push back, and so on. We're trying to implement a new stack interface that just has the concept of the top and pushing and popping from the top. One decision we need to make is whether to use a singly linked list or a doubly linked list. We have both at our disposal. Another decision we have to make is the correspondence between the concepts in the linked list and the concepts in the stack. So the stack manipulates just one end called the top. Linked lists have two ideas of the ends of the list, the front and the back. So these are similar ideas, but not exactly the same. Stack is defined in terms of the top and the bottom. Linked list has front and back. And we have to decide, how do these correspond to each other? Is the top of the stack the front of the list, or is the top of the stack the back of the list? And we could do this either way. We could implement it either way. So which one should we do? Well, we want a scientific answer here. This is the idea of asymptotic analysis. We don't want to just guess. We want to make a decision that makes sense based on reason and evidence. So we're going to look at the big O analysis of these two alternatives. Here are the relevant operations of linked lists. We have one column for singly linked lists and another column for doubly linked lists. Remember that most of the front and back operations take big O of 1 or constant time for both structures. Getting the front, getting the back, pushing to the front, pushing to the back, and popping to the front are big O of 1 for both kinds of linked list. The exception is pop back. Doubly linked lists can pop back in constant time. Singly linked list takes linear time to pop back because you need a way to get to the last node, and singly linked list doesn't have that. You have to skip past nodes. So if we make the top correspond to the front, then when we're pushing, popping, and getting the front, we're pushing, popping, and getting the top. Those are all constant time operations. Conversely, if we make the top correspond to the back, then when we access, push, and pop the top, we would be pushing and popping the back, and that means that the pop stack operation would take linear time, which is slower. So the decision here is that we should definitely have the top of the stack correspond to the front of the linked list, because if we do it that way, we get constant time operations for all of the stack operations. If we make the top correspond to the back of the list and we choose a singly linked list, then pop is going to be slow. In this application, there's no advantage to using a doubly linked list, so we prefer the singly linked list because the singly linked list has better constant factors. So here's the final decision. We're going to use a singly linked list, and the top of the stack corresponds to the front of the linked list. You can see that the top of the stack is the 1, and it's at the front of the list, not at the end of the list. This is consistent with that decision tree we had a while back in that video on choosing data structures. Right now we're committed to using a linked list of some kind, so we're down on the left side here, and the decision point is, do you need to remove from the back? Well, no. We're only manipulating the front of the list because that's where the top of the stack is, and the decision tree says use singly linked list. So that's consistent with that because the singly linked list has better constant factors in terms of time and space. Now let's take a look at a possible implementation of this. Here's the declaration. We've got a template class called linked stack, and one data member, which is just a singly linked list. So we're completely reusing the singly linked list class. We don't even need any additional data members. Singly linked list does everything for us. The default constructor will initialize that list to be empty. That works fine. To get the size of the stack, we just return the size of the list. And so these are one line, very simple functions that take constant time because they're just using singly linked list operations. And if you go back and check, the singly linked list constructor is constant time, as is the size operation on the singly linked list. Here's how we get the top of the stack. We've got an error check. If the stack is empty, there's no such thing as a top. So if size is 0, then we throw an exception. Our decision is that the top of the stack can be found at the front of the list. So we return the list front operation list front takes constant time. So top is constant time. Push is also a pretty straightforward one-liner. To push to the top of the stack, we push to the front of the single linked list. Note that there's no error check because this works even if the stack is empty at the moment, and it takes constant time because pushing to the front of a singly linked list is big O of 1. Finally, we've got pop. We have the same error check. If the stack is empty, you can't pop the top element. And to remove the top, we remove the front due to our correspondence. So we just do singly linked list pop front, and that's a big O of 1 operation. So pop is big O of 1. Before we move on, let's just reflect a moment on the reduction or reuse that's going on here. Reuse is the technical term for using predefined code to create new code. It's a good thing. And reduction is a more theoretical computer science term for using a predefined algorithm or data structure to create a new algorithm or data structure. They're very similar ideas. All of those member functions we just looked at were very simple. They were basically like one line or maybe 2 lines, very straightforward, no big ideas. This is a lot easier than some of the other data structures we've looked at. So the abstraction and encapsulation of singly linked list has paid off for us. It's a good thing. When we created that singly linked list, we were very careful to make reusable operations, push front, push back, and so on. And we encapsulated all those details of pointers, freeing memory, dummy nodes, all that kind of stuff is encapsulated, meaning now that we use the singly linked class, we don't have to think about it. It just works automatically for us, and that's a good thing. To summarize, here's the analysis of the operations. You can create a linked list stack, get the size, get the top, push to the top, and pop from the top. All of those take big O of 1 constant worst case time.